Hello everyone. Today we are going to discuss about the structure of an atom. We are going to understand different theories devised for understanding the atom, the nuclear atom, and the phenomena associated with an atom. Now, the modern physics comprises of studies of atom and related phenomena, and these are the basis for the foundation of quantum mechanics. Okay, so it is necessary for us to understand everything of our modern physics on the basis of quantum mechanics, of quantum physics. But one of the major setbacks of Nepal's education is that we have to understand this in terms of classical mechanics, in terms of classical circular motion, in terms of classical kinematics, dynamics, and everything. That is a major setback for us as students of Nepal. But since our colleges and our institutions force us to think in a classical classical way, we have been we have been trained to think of everything, every mechanism in terms of classical mechanics. That's why some of the phenomena that we are going to study today might feel somewhat bizarre or something. It's not because it doesn't make any intuition and we are talking about quantum mechanics, even though quantum mechanics doesn't make sense, not a whole of the quantum mechanics, but aspects of quantum mechanics doesn't make sense intuitively. But we are going to study very basic of them, so everything must make sense. And if it don't, that doesn't mean that it doesn't have a sense. It means that you haven't understood it quite well, because up to this level we haven't derived that much of quantum mechanics that would make us hard for understanding anything. Okay, so let's go through the topic. So we are going to start with the atom, but not from the very beginning, because if we go beginning, then we would have to go up to 1800s to understand the contemporary situations, which we are not going to do today. But let's start with Rutherford's experiment on alpha particle. So Rutherford was a teacher, and he was supervising two students of him, and he was supervising them for an experiment involving gold foil. So what he did is he used a radioactive source to uh, produce an alpha ray and strike it to the gold nucleus, and result he got various uh, mechanisms. Okay, and he found out that the nucleus, something called nucleus or proton, is in between of the structure and electron, and he devised a model by saying the electron revolve around the nucleus, and that theory of him led to a conclusion that if the electrons were to be revolving around the nucleus, then it might be the case, according to classical electromagnetism, that the electron must have been spiraling, must has to be accelerate, and the accelerating charge will spiral into the nucleus, causing the atom to be destroyed. But that doesn't happen. So to further modify this theory, Bohr came up with the idea of discrete levels of energy rather than a continuous flow of energy. And what he did is basically he introduced the Planck's idea of quantization of energy, uh, which was uh, which was thought to be a very niche idea, and it was thought to be a very particular idea to solve a particular problem. So quantum theory was not so uh, developed in such a level that everyone would agree on it. But Bohr, anyway, took that theory of quantized energy and devised it and said that in an atomic model, uh, the electrons are in a definite state of energy, and this definite energy and electron cannot be in between these definite energy levels. Okay, so energy levels were created uh, and to think of the atom, and on further modification, it was found that actually it was the problem of the finite structure, which devised the idea that if there was absolute one level of energy, then it was never possible. It would have been never possible for fine structures, even though spectral lines would be possible as a result of electrons from higher energy level uh, moving towards the lower energy level, emitting their energy in the form of light. But the fine structures, that means the breaking down of spectral lines would not have been possible according to the Bohr's postulate. So Arnold Sommerfeld came to rescue the Bohr's theorem, so not theorem, but Bohr's theory, and he said that actually, Bohr only considered a single principal quantum number, but we have to assume there are a lot of other quantum numbers, and and this single state of energy can also be further divided into different energy levels, and because of that, other transactions or other transitions of the spectrum line are also possible. That's why uh, finite structure is a phenomenon. Okay, so Sommerfeld did that, and along with that, Sommerfeld tried to find out the relativistic model of atom, which he couldn't. He drew a crude uh, atomic model, relativistic atomic model, but he couldn't uh, generalize it, or couldn't make a whole generalized theory out of it. But uh, then later came the what who Schrödinger, Heisenberg, Pauli, Dirac, and these physicists devised the whole quantum theory as a whole. Okay, and before them, uh, the who were they? Okay, so Willenbeck and Goldsmith or something. Yeah, so they were the one who found out that there lies something called spin in an electron. So electron also have a angular momentum, and also has an orbital angular momentum. Orbital angular momentum refers to the momentum when it revolves around the atom, and spin means whenever electron also has its own spin, and as a result of which it precesses, and that precision is what the spin is. The spin angular momentum account for. So these were the basic ideas, these were the basic outlines, how the theory was developed. All right. So let's go towards the basic and the fundamental ideas of Rutherford experiment. So Rutherford, as you already know, the experimental arrangement we have already studied. Now, what was the result? The result were that most of the alpha particles passed through the gold foil, okay, and most of the alpha particles scattered through the small angles. There were a few particles. There were a few particles that were scattered through the large angles, and a few of alpha particles were even scattered directly in the background direction or back direction. Okay. On the basis of the result obtained from the scattering experiment, Rutherford in 1911 fixed an atom as following. Atom consists of a central, highly dense particle called nucleus, where all the positive charge of an atom is concentrated. The size of the atom is of the order 10 to the power minus 10 meter, and nucleus is 10 to the power minus 14 meter. The nucleus occupies only a small portion of atom, and since the atom is electrically neutral, the positive charge in the nucleus is equal to the total negative charge in the atom, and the electron occupies the space outside the nucleus in an atom and revolve around the nucleus in circular orbits. If the electrons were at rest, they will be pulled into the nucleus with the strong electrostatic force of attraction between the nucleus and the electron, and the necessary centripetal force for the electron to revolve around the nucleus is provided by the electrostatic force of attraction between them. Okay, and what are the drawbacks? Drawbacks where the Rutherford model of the hydrogen atom is the nucleus of the hydrogen atom consists of only one proton, and the electron revolves around the nucleus in the circular orbit. The electron in the circular orbit experiences a centripetal acceleration. According to the Lorentz electromagnetic theory, an accelerated charge must radiate energy in the form of electromagnetic waves. If the accelerated electron loses all of its energy by radiation, then the total energy of the electron will continuously decrease and eventually becomes zero. And so it will spiral down into the nucleus. Thus, the atom cannot be stable. But it was well known that the most of the atom were stable. That's why according to the classical electromagnetic theory, the oscillating electron must radiate energy at a frequency equal to the mechanical frequency of the orbiting electron, and hence proportional to the angular velocity of the electron. Therefore, an electron spiral towards the nucleus, the angular velocity tends to infinity, and hence the frequency of the emitted electron will tend to infinity. This will result into the continuous spectrum with all the possible wavelengths, contrary to that we saw in the experiments. Like in the atoms, like hydrogen emit line spectra of fixed wavelength only. The theory of alpha particle scattering. Rutherford made the following assumptions for arriving at a relation describing the scattering of alpha particles by thin metal foils on the basis of his atomic model. They were the alpha particle and the nucleus with which it interacts are small enough to be considered as a point mass and charges. The nucleus is so massive as compared to the alpha particle that it does not move during the interactions. The scattering is caused by the repulsive electrostatic force because the nucleus and alpha particle is given by F equals 1 by 4 pi epsilon naught Ze to E by R squared. From these assumptions and the application of classical mechanics to the problem of the scattering of alpha particle by heavy nucleus, Rutherford devised the formula known as the Rutherford scattering formula. Now, there are 2 to 3 things that are very important to understand about Rutherford's model. First, he found out that the yeah, sorry for that. So he found out that if we consider that the electrons are moving in the speed nearly equal to the speed of light, then if we found that the radius of the nucleus, radius of the nucleus was 10 to the power minus 14, something times 10 to the power minus 14. Okay, because he thought that when an electron revolve around the nucleus, then the centripetal force of this electron is equal to the electrostatic force of attraction in between nucleus and the electron, as a result of which this balance, and the electron won't get directly into this nucleus, and atom won't be destroyed. But he forgot to keep the fact that even though electrons this centripetal force is balancing this electrostatic attraction. According to the classical electromagnetism, the the moving charge accelerates, and he couldn't keep the fact that it is accelerating. Okay, that's why uh, this Rutherford model failed at last. Okay, so and again, if you consider, so up to that point, I think the radius of atom was previously found out by J.J. Thomson, atom, radius of atom, not nucleus, to be 10 to the power minus 10. If you consider that, then the speed of electron would be significantly smaller than the speed of light. Maybe 10 to the power minus 4 times, 10 to the power 4 times smaller than the speed of light. And that's why, which can't be, because electron is assumed to be moving faster than that. So uh, that's why what we can, yes, and that's why the radius, this radius here, is not considered to be the radius of the atom, because it was already found out to be 10 to the power minus 10, but he thought that this radius must be of the radius of the nucleus, okay, which is 10 to the power minus 4. But it's a fact that now we know that 10 to the power minus 15 is the actual radius of the nucleus. But at that time, that was significant. This was significant. Okay, this was significant achievement by Rutherford scattering experiment. Now, this formula is what is known as the energy radiated per unit time by an accelerating charge. It will not change. It's a charge. Okay, charge is given by this. Energy radiated per unit time equals to this. So we can think of it as a power lost by an electron when it's revolving around the rotating orbit or circular orbit is given by this formula. And we can write this to understand that accelerating charges, that alpha is the acceleration of the charge, v is the velocity of the charge. So an acceleration charge, you can see the velocity is when the power is lost, the velocity will decrease, and as a result of which it would stop eventually at a time, and it would spiral. The formula of this would give a spiral curve, and the spiral curve will directly go into the nucleus, as of which the nucleus will destroy itself and become unstable. So this was the limitations of Rutherford. So let's stop Rutherford and the explanation of Rutherford model here, and let's go towards the board's explanation for these limitations. So these were the limitations. Now, to understand these limitations, actually to solve these limitations, Bohr assumed that when an electron is revolving around the nucleus, when electron is revolving around the nucleus, the Rutherford model has predicted that it would have a continuous energy. Okay, it would have a continuous energy, so it would gain as well as it would lose continuously, energy continuously. Okay, continuously due to the revolution. That means eventually the energy would be lost completely, and that would result the electron to go into the or bump into the nucleus and destroy itself. But Bohr assumed that there is no continuous energy. Actually, there are discrete level of energies on which the electrons reside. Okay, and that means electron. Uh, so since they are on the discrete levels of energies, what they would have. So how do I say it? Let me check. Okay. Yes. Classical mechanics says that whenever an electron is revolving around the nucleus, it would accelerate and it would lose its energy continuously sliding from high energy, and because the energy would continuously radiate, as a result of which the electron will lose all of its energy and bump into the nucleus. But Bohr suggested that instead of this continuous spectrum, continuous sliding down the energy, we have something called discrete level of energies. So even though, let's suppose we have energy in n equals 3. Let's suppose we have energy at third stage, third discrete level. Then if its energy loses its energy, and that loss of energy won't be continuous but in discrete path. So even though no matter how much energy the electron loses, it won't go below this n equals 1 level, because n equals 1 is the ground state. So if the ground state means electron won't have any energy. Okay, electron won't have any energy. So that's why electron won't lose any energy. And even though it's not losing any energy, it is not in the nucleus yet. That means this kind of thing, this kind of theory suggested that the electron won't lose all of its energy. Okay, and electron don't lose energy continuously. So that solves the problem of how electron can't bump into the nucleus, and and the atom cannot be destroyed all of a sudden. Okay, so that was the Bohr's postulate. Now Bohr's postulate considered first, the main characteristic of Bohr's model is first the energy levels discrete energy levels where the electron resides, and second one was the integral multiple h pi. So he said that the angular momentum of the electron must be integral multiple of h by 2 pi. Okay, now don't ask me how this h by 2 pi came, but h by 2 pi has a very interesting properties in quantum mechanics, because as you if you remember, uh, if you remember Heisenberg constant principle, I think this number comes frequently, right? And h by 2 pi, yeah. So this number, which is angular momentum, must be integral multiple of h by 2 pi. Okay, so this was the constraint that Bohr introduced. Okay, now discrete energy levels means the, each energy level or each electron in different energy levels will have certain amount of energy. Certain amount of energy means E equals h nu. E equals h nu, and this means that the energy which electron radiate is a quantity called quanta, which is the unit quantity in quantum mechanics. Okay, and this is it. Okay, all right. So what else I can say about this? Let me check. When we try to find out the radius of a Bohr's orbit, actually Bohr's we can now we already know that according to Bohr there are multiple orbits according to the energy they have. So if you want to find out, uh, okay, I think I should rephrase this statement as, if you want to find out energy or radius, the radius of the different Bohr's orbit from the nucleus, then you have to use this formula. Okay, and this formula is not very different. It doesn't come out of nowhere. It follows through the Rutherford's condition. Rutherford condition was this. And I just added the Bohr's postulate, which says mvi equals nh by 2 pi. So I found out v from here, and when I substitute v in there, in this Rutherford's formula, actually here, then I just got the R formula. Now we have got the expressions for velocity as well as radius here for Bohr's model. Okay. Now we can also find out the energy uh, by using a Bohr's other postulate, and let's find out the energy of different levels in according to Bohr's postulate. Okay. For the energy, you should understand that whenever we have an electron system which is revolving around the nucleus, the total energy of it is due to the summation of two different types of energies. First one, the energy of it due to the motion of it, and the second type of energy is due to the electrostatic uh, potential that the electron has. So that's why the total energy in an orbit of an electron, when an electron is moving in an orbit, is equal to the sum of kinetic energy plus potential energy. And we know that the kinetic energy has a formula of half of mv squared, and potential energy has a formula of minus of 1 by 4 pi epsilon naught e squared by r. And you know that minus means that electrostatic potential is pushing the electron to not towards but rather opposite from the nucleus. That's why we have minus sign there. Now we have already found out the values of V and R associated in Bohr's theory. So we substitute the values of V in this way, and we get a kinetic energy expression in this form. Similarly, if you substitute R in the potential energy, you will get an expression like that. Okay. Now let's add these two and let's find out the values. So for that, sorry, I think, okay, no problem. 1 by 8 m e to the power 4 epsilon naught squared m squared h squared minus m to the power 4 epsilon naught squared e squared h squared, and that is going to give us m e to the power 4 8 epsilon naught h squared e squared. So this is our total energy, okay, at any discrete level n. So we can find out the value of electron, or the amount of energy that electron must have to be in a certain energy level in Bohr's theory. Okay, so these are the three very important expressions regarding the Bohr's theory. One of the major advantages of Bohr's quantized theory, is that it seemed to be solving very long-standing problem of fine structures and the spectral lines. Now, people knew that spectral line exists, and they also knew that different electrons, so not different electrons, but different elements have different kind of electrons. Okay, so they didn't knew what the reason for the spectral line was. Okay, and since Bohr came up with the discrete energy level theory, so he could explain, or his model could explain, that whenever we have an electron on the high energy level and it goes to the different energy level, then it would emit a photon energy, which would correspond to a specific frequency, which would give us a specific color if it lies in between the visible spectrum, uh, visible spectrum range, that is 360 nanometer to 700 nanometer. That was a very quick and very good, not good, but it was a very useful uh, advantage of Bohr's model. Okay, all right. Now you have to understand one thing, that even before Bohr's explanation or Bohr's atomic theory of quantized states, these formulas were actually known. Okay, for example, so this formula was actually used by various scientists to find out the different spectral lines. For example, the Balmer series. The Balmer series, uh, found by Balmer, he used this formula. He used this Rydberg constant, which is not constant. Yeah, constant. Rydberg constant, this one, and he used this to find out, or okay, so he used the values 2 and 1 just by trial and error. Okay, he didn't know about these discrete levels. Okay, so but he found out that if you put 1 here, if you put 2 here, uh, that is Lyman. So Balmer is 2 to 1, right? Okay, so no, no, 2 to 1 is Lyman, 3 to 2 is Balmer. Yeah. So he, by trial and error, he found out that if you put 2 here, if you put 3 here, he would find out a wavelength one, and he found the values of he found out the lambda. He found out that lambda was equal uh, to the light of the light that was in the spectral line. So he did that, but he didn't know the actual meaning of this formula, and it was Bohr who explained, who interpreted the hydrogen spectra. Actually, hydrogen spectra, uh, is he said that these are just the transition of electrons in different energy levels. Oh, sorry. Balmer series means any of the electrons upper than the n equals 2 shell. When these transit to this n equals 2 shell, then that type of transition is called Balmer series. Okay, there is something called Bohr's correspondence principle, which says that the new atomic laws, according to the contemporary time, is said that new atomic laws must be in such a way that the uh, classical mechanics rules must satisfy the quantum rules when n tend to infinity. That means when the number of cells or number of orbits tend to be larger, then at that time, the quantum mechanical rule are equal to the classical mechanical rule. Okay, to frame that in a uh, much better way, in 1932, Bohr pointed that the new laws of atomic mechanics required to describe the motion of the subatomic particles like electron inside the atoms have to be developed in such a way that these laws must go over the laws of the classical mechanics and the limit of larger microscopic bodies. This is known as the Bohr's correspondence principle and forms an important clue in formulating the laws of atomic mechanics. Since the orbital radius of the electron becomes very large when the quantum number n is very large, the laws of classical mechanics should be appreciable in these cases. In other words, according to the correspondence principle, the result derived from the Bohr's theory should go over those deduced from the classical mechanics in the limit of very large quantum numbers. Alright? To test Bohr's correspondence principle, let's do something. What I did here is, we know that the frequency of any, okay, let's suppose electron revolving around the nucleus is given by, or any in a circular orbit, the frequency, angular frequency is given by v by 2 pi r. Now, what I did is I used the Rutherford's condition and I found out the values of r and v for the Bohr's condition as we did previously. Then I substitute the values of v and r and I found out this to be this. Okay, so this is what the mu is. That means the angular frequency is. Let's find out the same thing, the angular frequency, but not as the quantum mechanical way, but in a classical way. Okay, classically, frequency of the radiation emitted due to the transition from n plus 1 to n state is given by nu equals omega by 2 pi, and we already know that that is given by, in fact, the Rydberg's formula for different kind of series, transition series. So if you now we know we have considered n plus 1 to n, that means large number of states, which must approximate the Bohr's condition here for the frequency. Okay, now let's see. So it can be solved in this way, and now we know that since n is very large, so we can approximate n plus 1 to be n and 2n plus 1 to be 2n. Then if we do that, we would get the same condition. So which verifies the Bohr's correspondence formula. All right. Now there is a very important experiment done to actually to check the Bohr's formula, and the intention was the Bohr suggesting discrete energy level is just in their language a nonsense. Okay, nuisance. So according to them, so that's why they wanted to show that the Bohr's theory doesn't hold any truth. So that's why Franck and Hertz did an experiment, uh, which is now known as a Frank-Hertz experiment, and it turned out that this experiment was actually actually became the proof for discrete energy levels. Okay, so let's see this one. So this was the experimental apparatus for Frank-Hertz experiment. So what they did is they had a filament which is used to generate electrons, and they had a chamber, a cylindrical tube, where they not fit, but where they put uh, Hg vapor at low pressure. Okay, and the the, the what is it called? The purpose of the Hg vapor is to is because we are trying to find out the excitation potential of this Hg vapor. Okay, now when we run this apparatus, then this voltage would heat this filament, and electrons are produced from this filament, and these electrons, since we have a voltage here in between this filament and this cathode, okay, this anode and this cathode, so these electrons would try to go there, okay, to complete the circuit. So as the accelerating potential has increased from zero, so this is the accelerating potential when we so this is the accelerating potential, and when we increase this accelerating potential from zero, the current at C will increase until it reaches a characteristic excitation potential of the vapor. Okay, so what happens is when we increase the exciting potential of this, then the current at C increases. Okay, now I'm going to try to explain what phenomenon is going on in our Franck Hertz experiment. It's a very beautiful experiment. And when I learned first about it, I was very amazed that such kind of thing could happen in nature and can be appropriately captured by such experiment. So let's see this one. So what happens is, so I have already described the apparatus. Now remember we have two potentials here. First potential is accelerating potential and second potential is retarding potential. Okay. Now retarding potential means a small amount of potential which act as a barrier, and whenever there is a when the incoming electrons will have much energy, then this redirecting potential, then only they can go or they can complete the circuit. Okay, which doesn't have any role here actually. So we have this setup. Okay, now what happens is first thing you should notice here, or first thing you should know here, is that we are continuously increasing our accelerating potential. Okay, we are continuously increasing our accelerating potential. And so let's see what the phenomenon looks like. So we increases the potential, and this, since the filament is already burning or heating, that's why we will get electrons coming out of this filament. Now electrons would go to that, and if the electrons have sufficient amount of energy, they would break this retarding potential and complete the circuit. That is a natural thing that should happen. But what was found that at a particular level of energy, at a particular point of energy, that let's suppose at 4.9, for actually 4.9 for mercury vapor. So at 4.9 for this mercury vapor, something unusual happened. We would assume that whenever we increase the accelerating potential, collector current would increase because the electrons will have more and more energy, since that's why it would run over the circuit and would have more current. But what was seen what was seen is that at particular value at 4.9 volt, we got a decline, or we got a decrease in our current. And after a certain time, when we increase our accelerating potential continuously, after a certain point, it increases. And again, at integral multiple of 4.9 means 9.8 volt, it again dropped. Again, at the integral multiple, 3 times 4.9, okay, 3 times 4.9, at this at this value of accelerating potential, it again dropped. So this is what was the observation of this experiment was. So it was very fascinating, and it was very riddling what's going on here. So it turns out this is what's actually happening here. So what's happening here is at a particular level. So let's suppose we have 4.9 volt. At 4.9 volt, this mercury atoms, mercury electrons in the atom, or atom of the mercury atom. Okay, in a mercury atom, the electrons of mercury, when they get 4.9 volt energy, then that completes one quanta energy that they require for for transitioning from ground level to the excited level. That means now these were there. These mercury vapor atoms were there, right? Now the electron will continuously hitting them, but at that point the collision was elastic. But when these electrons have sufficient amount of energy, which is 4.9 volt, then these mercury atom get 4.9 volt, and the electrons inside the atom not increased, but transitioned from the ground state to the excited state. So that's why leaving behind these electrons with barely sufficient energy to overcome this retarding potential. That means we won't have any current following flowing through the circuit. That's why we will see a certain drop. Now, since we are increasing our accelerating potential continuously, that's why we will again see an increase in our current after some time, because this filament is continuously producing electrons. Now, even though the electrons, these electrons, the previous set of electrons, have lost their energy, this new set of electrons will go there and flow through the circuit, and the current will increase. Again, after a certain time, either either the remaining atom will excite from ground state to the higher energy state, or this excited state, the excited electrons will again go into some transitions. Okay, now that after that transition, okay, so one thing I forgot to mention, that this increase in current is not only because new electrons are going there, but it's also because, since after getting excited, they won't these electrons won't be living there forever, so they would go there go to their ground levels, and they would release some energy in form of anything, in form of heat, light, anything, and that energy is again absorbed by this new set of electrons. So that's why you get a sudden jump in the energy. Okay, so that is what's going on here. So it proves that this proved that at a certain particular integral multiple of a particular characteristic excitation potential, at a integral multiple of characteristic excitation potential, we would get these drops, and sudden increase is a result of inelastic collision in between the mercury atoms or ions, and the electrons. So that is what the explanation of Franck Hertz experiment is. So this Franck Hertz experiment actually verified that there exist discrete level of energies in any atom. Okay,